So welcome to IGAFIT Algorithmic Colloquium. And before we start, let me remind you to subscribe to the mailing list, Twitter, and Facebook to get to know the coming talks. I will post the link on the chat after this and you can just click the link and see more details about this. And also, let me remind you that there will be a social session after the talk, so please stay tuned to say hi to the speaker and colleagues. And in case you have question, there is a question tab on the right side. So please submit the question there and let me know if you have, if you want me to bring you on stage, so you can ask the speaker the question yourself. All right, so now let me introduce Jason briefly. So in case you don't know Jason, he's a final year PhD student at Carnegie Mellon University. And for one thing, he won the Best Student Paper Award at Fox 2019. And today, he will talk about the recent breakthrough on computing minimum cut deterministically, and this work will soon appear in the coming talk. So Jason.
Thanks for the introduction. So this talk will be on deterministic mincut in almost linear time. And this was work done while I was visiting Microsoft Research Redmond. And I'm grateful to Sivakan Gopi, Janardhan Kulkarni, Yakov Tarnovsky, and Sam Wong for hosting me while I was an intern there. So a more accurate title of this talk would be a structural representation of the cuts of a graph. And this will actually be our main focus for the talk, and we'll see the connection later on, why deterministic mincut requires a structural representation of the cuts. So in this talk, all graphs are going to be undirected and unweighted. And we'll be considering the global mincut problem, which is given the graph, find the minimum number of edges to delete to disconnect the graph. So a classic algorithm by Karger and Stein shows that we can just iteratively randomly contract edges of this graph to get an n-squared algorithm. Another classic algorithm by Karger is achieves a near linear time for this problem, and this is by sparsification plus tree packing. And we'll see this later on in the talk. Karger asked in that same paper whether a deterministic near linear time algorithm exists. Back then, the best time was m times n, which is far from linear. And this question was recently partially answered by Goranci and Thorup. They showed a near linear time algorithm for simple graphs, and these are graphs that are unweighted and have no parallel edges between vertices. I, along with Damania Panagrahi, presented some progress on this problem in the general case. We show that a deterministic mincut reduces to polylogarithmic calls to exact max flow. So this breaks the MN barrier, but does not yet achieve linear time because St max flow is not known how to be solved in linear time. And finally, in this talk, we use a different approach, and we achieve near linear time by essentially de-randomizing Karger's algorithm based on sparsification tree packing. And along the way, we'll see that in order to de-randomize this algorithm, we require a structural representation of cuts, and we'll present such a representation in the talk. And by the way, most of these results also works for weighted graphs. So in particular, this result on deterministic mincut also works for weighted graphs. But for the simplicity of this talk, we'll be considering unweighted graphs. So how does Karger's algorithm work by sparsification plus tree packing? So Karger's first idea is, suppose that we're given a skeleton graph. And this is a graph that satisfies the following three properties. H has roughly at most number of edges of G. The mincut in H is small. So note that the mincut in G does not have to be small. Essentially, the mincut, the reason why it's called skeleton is because the mincut gets reduced to a small factor, n to the literal 1. And finally, we want to say that the mincut roughly preserves the graph H roughly preserves the mincut information in G. And more formally, this means that given the mincut in G, suppose a delta G S star is a mincut in G, where S star is a subset of vertices. So delta G is just a boundary of the edges. Then this same mincut, the same vertex partition, the same cut, the same vertex partition in H is a 1.1 approximate mincut in H. So suppose we are given a skeleton graph H that satisfies these three properties. Then we can compute an exact mincut in essentially near linear time, additional time, given this skeleton. And the algorithm given the skeleton simply computes what is called a tree packing of a small number of trees into H. So what is a tree packing is essentially a collection of trees that packs along does not contain a single edge in the tree in the graph too many times. And it's known that if we compute such a tree packing, then one of these trees will to respect the mincut in G. So we'll pack the trees in H, and one of these trees will actually to respect the mincut in G, where to respect means at most two edges of the mincut cross at most two edges of the tree cross this mincut. And finally, Karger developed an algorithm that, given a tree and the original graph, computes the minimum to respecting cut in the linear time. So all these together, in addition to computing the skeleton graph, which we have not discussed yet, gives you the near linear time algorithm. And the nice thing about this algorithm is that it's deterministic. Everything here is deterministic. And Karger, and the only randomized component in his algorithm is computing this skeleton graph. And he does it via graph sparsification. So in particular, he computes something even stronger. He computes essentially a 1 plus epsilon approximate cut sparsifier, which turns out to suffice for this third condition. And here we define a cut sparsifier to be, there exists some scaling factor W. So imagine that every edge in the cut sparsifier is weighted by W, such that for any cut, for any set S, the vertex partition, the size of the cut in H times the scaling factor W is roughly up to 1 plus epsilon, the cut in G. So in particular, this preserves all cuts in the graph, whereas here we only need that the min cut is roughly preserved. And that's a stronger property. So our goal will be to de-randomize this skeleton graph construction. And in order to do that, let's first examine how does Karger's randomized skeleton graph construction work. So his is very simple. All you do is you sample every edge independently in G with probability, let's say like log n over lambda times some scaling factor. And let H be the sampled edges. Then he shows that with high probability, every single cut satisfies the size in H is roughly P times the size in G, where you can think of P times the size in G as the expectation of the cut. So in other words, every single cut in H is roughly preserved in expectation, preserved close to its expectation. And the proof requires essentially a smart union bound over all the cuts. So suppose we fix some parameter alpha, and we consider all the cuts of size at most alpha times lambda, where lambda is the mincut of the graph. It's known, a well-known result of Karger and Stein shows that there's at most n to the 2 alpha in many of these cuts. And now for any given cut, the probability that this guarantee fails is by a simple Chernoff bound at most 1 over n to the 3 alpha. Now it's important that this is n over 3 alpha, which will eventually cancel out n to the 2 alpha. Because we can just take a union bound over all n to 2 alpha cuts and get the probably some cut of size roughly alpha lambda fails is like 1 over n to the alpha. And finally, we can union bound over all alpha and get like total union bound of 1 over n, which is small enough. And we can always boost this 1 over n to like 1 over polynomial. So how do we de-randomize such a construction? So this turns out to be a lot harder than when you think a little about it. And in particular, even verification is hard. So suppose we have a sample. How do we even verify that the sample is correct? That satisfies this guarantee? Well, there are 2 to the n cuts to check. So this is not even polynomial time checkable. You have to check in estimational time. So in other words, the difficulty in de-randomization or even verification is we need to union bound we need to formulate the union bound more efficiently. So we don't want to union bound over all the cuts separately. We want to find some more efficient way to characterize all the cuts in the graph. So this is where our main insight is to develop some structural representations of the cuts, so we can more efficiently union bound over in the argument of Karger. So in my opinion, this is why de-randomization of algorithms is interesting to me, because in this case, while a randomized algorithm can just union bound over this large collection of cuts, de-randomizing the algorithm requires developing some structural insight to these objects. In this case, the cuts in the graph. So I think, in my opinion, this is why we should care about deterministic algorithms. So what are potential approaches to figuring out a structural representation of cuts? So there's one known approach, and it's a spectral approach. H is a 1 plus epsilon per cut sparsifier if the following condition holds. If you take the Laplacian of a graph, we'll define this later on in the talk. But for now, the notion is not super important. If the Laplacian of the graph is roughly, if the Laplacian of the sparsifier is roughly the Laplacian of the graph. And here, the reason why it's called spectral is because it's based on the eigenvalues of the Laplacian. So in particular, the eigenvalues are up to 1 plus epsilon of each other. Right? And this led to a deterministic sparsification routine by Batsman, Spielman, Svertava but the running time was pretty large. And turns out if you apply randomization, you can bring this down to near linear time. This is a result by Lee and Sun. And so far, the only ways of de-randomizing graph sparsification that we know of require this special approach as a way to understand this representation of cuts. In this work, but unfortunately, the best deterministic running time for this special approach is still n times n cubed, and that's far from linear. So we develop a second different approach. We have a combinatorial representation over the cuts of a graph, and this is via expander decomposition. So this is the first combinatorial approach to characterize the structural representation of graphs. So for this rest of the talk, we'll first give a quick roadmap on what's to come. So the first thing we'll actually do is we'll actually consider, suppose the input graph G is an expander, and see how do we compute a skeleton graph for an expander. And along the way, we'll answer the question, why are expanders easy? So why should we consider expanders first before generalizing to all graphs? And now on the first step into generalizing all graphs, we'll first consider what's called an expander of expanders. We'll see this later on, and we'll encounter some difficulties and additional challenges in how to generalize from an expander to this expander of expanders. And finally, for the general graphs, we'll see how to apply our expander decomposition on the graph to get the full result. So let's begin with expanders. For expanders, we'll need two crucial definitions. The first is the conductance of a graph. So conductance is a parameter, which is a real number, and it's equal to the minimum over all cuts in the graph, where we only consider the side that's has smaller volume. And here, volume means just the sum of the degrees in S. And what we're looking for is the size of the cut divided by the volume. So in this case, the size is 1, and the volume is just the sum of the degrees, which is 7. So it's 1 over 7 in this case. And G is a phi expander for some parameter phi if the expansion is at least phi. Now, why expanders? The result of Goranci and Thorpe showed that in their near linear time deterministic mincut for simple graphs, they showed the following crucial connection between expanders and mincuts. It's that in a phi expander, any alpha approximate mincut must have essentially a small number of vertices in its smaller side. So here we'll define a alpha approximate mincut as a cut of size at most alpha times lambda, where lambda is the mincut. And here we must have, let's define S to be the smaller side of the mincut. We must have this side has at most alpha over 5 vertices. So what does this mean? Before we go to the proof, what does this mean? This means that we have essentially we already have a structural representation of near mincuts in the graph. They're just all the cuts that are very unbalanced. All the cuts whose smaller side has the most alpha over 5 vertices. And this is a superset of essentially all alpha approximate mincuts. At least we haven't obtained a structural representation of all cuts, but at the very least we have obtained a structural representation of all alpha approximate mincuts. And it has a very simple structure. It's just, again, all the unbalanced cuts. So why is this? Finally, let's go through the proof of why this claim is true. It's very simple. Suppose, without loss of generality, that the volume of S is at most the volume of B minus S. So we're picking the side of the mincut, the side of the cut of a smaller volume. So the volume is by definition the sum of the degrees of the vertices. This should be B here. Sum of the degrees of vertices. And now every single vertex can induce a cut itself. So for each vertex, we can just delete its neighbors, and that gives us a cut. This cut must be at least a min cut. So that means that the degree of each vertex must be at least lambda. So we get lambda times S, the size of S. And finally, we plug in our the expander definition. Phi is at most conductance, which is at most for this particular this expression here. And here, by definition, the number of edges is alpha times lambda, and the volume is at least lambda times S. And then finally, we can rearrange to get our desired bound on S. So this proof essentially captures the intuition of why expanders are useful, why the relation between expanders and mincuts of the graph. So given that insight, how do we build a skeleton of the graph? So first, let's not try to preserve all. Let's try not to get a full skeleton of the graph. Let's first try to ensure that for all unbalanced cuts, so these are cuts where the smaller side has the most alpha over 5 vertices, that the cut in H is roughly up to 1 plus epsilon, P times the cut in G. Recall that P times the cut in G was just the expectation. So we're using the same factor P as Karger used in his graph simplification. And as a first step, we'll just ensure that this is true for all unbalanced cuts, and will not make any consideration for balanced cuts so far. So here's our key lemma in this case. We claim that it suffices to ensure these two claims. The first claim is essentially a degree preservation. So we want to show that the degree of each vertex is roughly P times this degree in the G, plus or minus some small additive factor. And second of all, for any two vertices in the graph, the number of parallel edges, this is defined as the number of parallel edges between U and V in H, is roughly, again, its expectation plus or minus some small additive factor. By suffice, we mean that if we can satisfy these two conditions, then actually we satisfy our goal. So if we can satisfy just these two conditions, then we get the preservation property for all unbalanced cuts. What's nice about these two conditions is there's only n plus m constraints here. So recall that the set of unbalanced cuts is still pretty large. It's like n to the alpha over 5. It's still a large collection of sets. We cannot union bound over all of those. But these two conditions, there's only n plus m constraints. Why? It's because the first one is clearly n. The second one, well, we only really care about U and V that are edges in the graph. Right? Because if U and V is not an edge in the graph, then the first quantity is 0, the second quantity is also 0. Because again, we never sample edges that are not in the graph. So there's only n plus m constraints, and this is already, you can think of it as a more efficient union bound over the cuts in the graph. So what is the proof? The proof relies on the concept of graph Laplacian, which is an algebraic representation of cuts. And here, so how it works is suppose we have a graph. The Laplacian is indexed by the vertices of the graph on its rows and columns. And now for a diagonal entry, the entry is simply the degree of the vertex. And for an off-diagonal entry, it is the minus negative of the number of parallel edges between the two vertices. So x and y in this case. And what is nice about the Laplacian is it represents cuts well. Cuts have this following nice form. For any set S, the cut the cut of the boundary of S, the size of this cut is this following. This is essentially this nice expression, where indicator of S is the vector on the vertices, where it is 1 if if the vertex is an S and 0 otherwise. Which is 0, 1 vector. That's essentially the indicator of S. And now why is this useful? Consider some unbalanced cut S. So the size of the most alpha over pi. Then we can write the size of the cut in H, again using this equality. But now we replace indicator of S with essentially just the sum over all V of indicator of V, which is clearly the same. And now let's expand this summation in this expression, and we get this. Now, what is indicator U, L, the Laplacian of H times indicator of V? Well, by definition, that is just entry UV in the Laplacian of H, which essentially by definition becomes this. Now, the key observation is the summation only has alpha over phi squared terms. So if we can ensure that each of these terms is preserved up by is preserved to its expectation up to this like small additive factor, then we know that by just summing up these additive factors, we know that overall the entire expression is preserved up to this epsilon times lambda. And now since the original cut itself must be at least lambda, this is a 1 plus epsilon approximation. That's essentially the proof of this more efficient union bound over the unbalanced cuts of the graph. So I'll give a brief overview. This will not be super important to talk, but I'll give a brief overview of how we actually get a deterministic algorithm out of this. How to actually de-randomize the randomized construction. And this is via a concept called pessimistic estimators. And here's the very high level overview of how this works. So for each of the two constraints, for each of the n plus m constraints, we essentially compute an upper bound on the probability that the constraint fails. So this upper bound will be based on a Chernoff bound on essentially the events the failed events. And essentially by the randomized analysis, we know that the sum of all the union bound over all these upper bound probabilities is much less than 1. And this is just by the same analysis of the randomized algorithm. And now, given an edge E, so we'll actually loop over all the edges in the graph in order. And for each edge, we'll determine on the spot whether to include that edge in the Sparsifier or not. Now, given each edge, let's try to update the probabilities, the upper bounds, the Chernoff bounds, as conditional on whether we choose or skip, on choosing E. And let's try to update it on conditional on skipping E in a Sparsifier. And now note that this is efficient because there's only 3 constraints in this collection that contain E. They are just for edge UV, they're just U and V in the first constraint, and also edge UV in the second constraint. And now we just choose or skip E in this Sparsifier depending on which conditional property is smaller. Does choosing E lower the conditional? If the choosing E lowers the conditional probability, then we choose E. And if skipping E lowers it, then we skip E. And it turns out one of the two will actually always lower the conditional probability. And at the very end, once we've made all our selections, the final upper bound is still at most 1, still less than 1. And now, since there are no more deterministic choices to be made, everything's we've essentially covered all the randomness in the construction. That means that essentially nothing must fail. because every probability of failure is either 0 or 1. And if everything's less than 1, then everything's 0. And we get a deterministic construction. Yeah, that was very high level, but it's not terribly important to talk. So now this essentially covers all unbalanced cuts. But what about balanced cuts? So the sample graph we consider, it can preserve all unbalanced cuts, but there might still be a balanced cut in the graph that's not preserved, and this is not good for us. And that's because let's recall that what do we want? We want that for the mincut in G, the corresponding mincut is a 1.1 approximate mincut in H. In this case, let's suppose the mincut, which is this degree cut, then this cut is no longer a 1.1 approximate mincut in H because this balanced cut is much smaller. And that's something that we do not want. We don't want much smaller cuts that are potentially balanced in H. So here's our second insight in this construction. Our goal will be just to essentially to force the balanced cuts to have large weight. And here, p times lambda is chosen so that, recall that we should expect the mincut in H to be roughly p times lambda. So if we can force the balanced cuts to have weight at least p times lambda, then this essentially prevents any cut in H to have size much less than p times lambda. And this will mean that for the optimal mincut in G, the corresponding cut will now actually be a 1.1 approximate mincut in H. So how do we accomplish this? We essentially overlay some arbitrary expander into the graph. So we take the sparsifier H and we union it with some arbitrary expander, and we do it in such we weight it in such a way that the mincut of G increases by a small amount, by a relatively small amount. So here by epsilon p lambda, which is just like epsilon times its size in H. But any balanced cut increases by a much larger quantity, and increases by p times lambda. And why is such a guarantee feasible? Well, because balanced cuts are balanced in the graph, and in an expander, the balanced cuts have much larger size. So all we need to do is ensure that the balance parameter is large enough that these balanced cuts have many more edges in this arbitrary expander than the mincut, which is an unbalanced cut. So as long as the gap is like epsilon to 1, then we can guarantee such a result. So let's recap of what we did so far for expander case. The theorem essentially had two main parts. The first is we preserve all the unbalanced cuts up to a factor 1 plus epsilon by essentially all we need to do was preserve degrees and the parallel edges, and this was an efficient union bound essentially that we were able to satisfy and imply that all unbalanced cuts are preserved. And in the case of balanced cuts, we don't know how to preserve them up to 1 plus epsilon. So instead, we just overlaid expander in the graph, which forced all these cuts to be large. This meant we no longer had a 1 plus epsilon approximate Sparsifier, but this still worked for the Mincut application, for the skeleton graph. So next step, let's consider what I call an expander of expanders. This is like essentially the next step towards the full generalization to all graphs from an expander. And here, so what does it mean for a graph to be expander of expanders? Suppose we partition the vertices of the graph into expanders, into induced expanders, where each expander I think of as like a phi expander, where phi is some parameter. And now, suppose we contract each of expanders into a single vertex. Then the resulting graph is also an expander. So that's what it means to be an expander of expanders. And note that essentially here, what we have is we essentially have an expanded decomposition of G, which is defined to be, again, partition of vertices such that the induced expander on each part is an expander for all I. So let's try to generalize the expander case to the expander of expanders. And this raises a few questions. First of all, so the first step for the unbalanced case, how do we develop a structure of unbalanced cuts? And here it's not even clear how to define unbalanced. What does an unbalanced mean in this case? So that's actually a question we need to answer first. So let's try to answer how do we define an unbalanced cut in expander of expanders. So suppose we have a cut S, the blue cut S. Let's say S is the left side. So the first thing we want to do in this for this cut is we want to essentially align. So this cut can cut into some expanders. Our first step is we want to force this cut to align with the expanders. So for each expander, either it has to be completely on one side of the cut. So in this green cut, what we did was essentially align the cut with the expanders, where for each expander, whether we choose to shift it into the cut or out of the cut, we just choose like the one that results in the smaller number of vertices being shifted. So in this case, we just shifted these smaller sides over. And here, let's define D as a difference, as the set of vertices that we either added or deleted to S in the alignment. And now, the nice thing about aligning an expander with expanders is that once we contract, the cut stays. So once we contract each expander, this cut delta S prime becomes some other cut, let's say delta S2, in the contracted graph. And we can define S2 as essentially, again, the smaller side, the left side. And now this leads to our definition. We define as cut S in G to be unbalanced if the set D that we constructed was at most alpha over pi. In other words, we shifted at most alpha over pi vertices in total. And in addition, we want that in the contracted expander, essentially this blue cut is an unbalanced cut in the traditional sense. So we have once we contract, we're left in an expander case. We want that the cut S2 that we obtain is what we called unbalanced in that case. So its size is at most, the number of vertices is at most alpha over pi. So why is this definition of unbalanced useful? Why does this lead to a corresponding construction for this expander of expanders case? Well, let's define S. Let's define the cut S in the following way. So what we do is for each vertex in the expander, in the contract expander, let's define V bar as what we call a pre-image of V. It's all the vertices that contract into V. So in this case, it's just like the vertices in the corresponding expander. Now we can write S in the following way. We can say S is equal to take the disjoint union of all the pre-images of all the vertices in S2. So essentially, this gives these three expanders. But now we need to take the symmetric difference with essentially the vertices we shifted in the alignment process. So once we take the symmetric difference, then we recover the original cut S. And now again, let's write the cut of the graph in G, the cut of S in G, as this Laplacian form. Where in this case, we write the indicator of S using this representation. So it's equal to the sum over V in S2 of the indicator of the pre-image plus the sum over all the vertices in the difference of either plus or minus indicator of U, where plus or minus depends on whether we added or deleted that vertex. The whether it's plus or minus does not really matter in our case. We'll see why. And again, by definition of unbalanced, we get that each summation has the most alpha over pi terms. So what we get is if we expand this expression, we get at most, again, O of alpha over phi squared terms. And each term is the form indicator X, LG indicator Y, where X and Y are either pre-images of vertices in S2 or original vertices in the graph. And what does that mean? That means we have a sufficient condition to satisfy for all unbalanced cuts. We just need to satisfy these conditions. So for every expression of the following form, where X and Y are either pre-images of vertices in S2 or in V2 or original vertices in V, we want to preserve this quantity here. And it turns out how many constraints do we have? Turns out we still have n times n. Why is that? That's because every edge in the graph, in the original graph, belongs to at most 4 of them. That's because for a given edge, either its either the endpoints are either the original two vertices, or they're contracted or they're contracted versions. There's only 2 choices for each endpoint. That's 4 in total. So there's still only like 4 times n plus n constraints total, and this gives an efficient union bound that preserves all unbalanced cuts in the graph. And finally, for the balanced case, we do something very similar. In the expander case, we just overlay the expander. In this case, we want to overlay essentially an expander of expanders. So we just overlay expander in each expander of the graph. And then you imagine like contracting it, taking an overlay of the contract expander, and then kind of just like pulling it back to the original graph, where if you attach an edge in the contract expander, then we just attach an edge arbitrarily between the two corresponding expanders. So we overlay some expanders to ensure that all balance cuts become large in size. And this expander of expander construction can be generalized further into a recursive expander decomposition. Essentially, we take a graph, compute an expander decomposition, which is a way to partition the vertex set into parts, such that the induced expander on each part is a phi expander. So this can be done efficiently deterministically. And then, given the expander decomposition, we contract each expander and just repeat the process. So we compute another expander decomposition, and then contract the parts, and so on, until we're left with like a single vertex, let's say. And so 2 properties we need to guarantee from this expander decomposition is, first of all, we want to make sure that the number of levels of this is bounded. Like at least this process should terminate after a small number of steps. So this can be guaranteed by this property of intercluster edges. So these are the number of edges in between clusters and expander. It turns out we can guarantee that the number of intercluster edges of the expander decomposition is roughly, this should be like roughly, a phi fraction of all edges. So it's at most phi times m in the first iteration, and that means it's at most phi squared times m in the second iteration, and so on. And this ensures that there are only log to the 1 over phi m levels before there are no more edges left. So at least this bounds the number of levels of this recursive expander decomposition. And finally, we require what is called boundary linked. We require something additional. We require what is called boundary linked. We require an additional boundary link property for expander decomposition to upper bound. Essentially, this will upper bound. This will upper bound how the cut grows over time as we like shift the cut to align with expanders. So this is like a technical property that we're going to skip in this talk. And by the way, this boundary linkness property was introduced in this recent paper by Goranci, Rake, Saranurak, and Tan in SOTA 21. I forgot to add a citation here. But so this is a very important property. We won't see why it's important in this talk, but this turned out to be necessary. So that's it for that essentially concludes my talk. As a recap, we obtained a deterministic mincut algorithm in nonlinear time by de-randomizing the skeleton construction in Karger. And a few open questions. So what's left open from our work is a deterministic 1 plus epsilon approximate cut specifier, which I think is a very interesting interesting question, because it requires kind of completing the picture of our construction, which is understanding the structure of balance cuts. Now we fail to understand we failed to accomplish such a thing because we just overlaid an expander, and that kind of destroyed the 1 plus epsilon approximate guarantee. So I think in order to de-randomize, to fully de-randomize 1 plus epsilon approximate cut specifier, it requires some new insight on the structure of a balanced cuts in the graph. Or potentially the solution could be taking a different approach, taking the special approach. Recall that the special approach has a near linear time algorithm for the randomized case by Li and Sun, perhaps the right solution is to just de-randomize their conversion. But this also seems to be hard. At least we've tried. From our experience, this also seems to be hard. And finally, another question is, can we improve the running time of deterministic mincut to m times polylog, which would fully match Karger's randomized construction algorithm? Finally, is there a deterministic mincut in m times polylog time? This would match Karger's randomized construction, randomized algorithm. And here, one bottleneck is we actually don't know how to compute experimental decomposition in deterministic with polylog factors. So m polylog time and polylog in the approximation. So such an algorithm will either require a faster expanded decomposition or just bypass expanded decomposition to be completely. So that, yeah, I don't know what seems to be like the right approach there. Yeah, so that concludes my talk. And thanks for showing up.
So thank you, Jason. Does anyone, and let's give a hand to Jason. So anyone have a question? You can also type in the live chat or raise your hand. Yes. Somebody raised their hands, but it's disappeared now. So meanwhile, in case while we waiting for question, let me ask one question for now. So is it the case that if you get polylog and factors for expanded decomposition, then are we done, or we actually need something more? Because it seems you need this
there's
hierarchy.
Still something. There's still like a 2 to the square root log factor that we get based on this boundary linkness. Yeah. So
basically, if we can make the work by Goranci et al. M polylog n instead, then we will be done.
Turns out we will not be done yet. There's still a factor. There's still like this blow up factor that we get from this boundary link property. So it's more complicated than that.
And I see. So Amir Abu asked a question. Thanks for the talk. Can you explain again what is the boundary link?
I can go through very informally. So it's essentially if you're familiar with like this boundary linked. Is it called boundary link? So I know like Roque had a few papers that investigated this boundary linkness condition. Essentially, it means that if you take an expander and take the boundary of this expander, for any cut in the expander, so take a cut in the induced expander, the number of boundary edges adjacent to incident to this cut should be not too large relative to the size of the cut in the expander. So I'm not sure if that was a good explanation, but another way to see this is we can establish like an all-to-all flow from the boundary of the expander to each other. So the boundary of the edges of the expander to each other. So every edge in the expander can send like flow to every other edge in the expander, and this can be done with small congestion in the induced expander. So that's like the flow representation, and that pretty much means that any cut,
the flow can go outside.
Yeah, it cannot go outside. It cannot be inside the expander. That pretty much means that any cut in the graph must be relatively large. Must be large relative to the number of boundary edges on the smaller side, incident to the smaller side. Yeah, so essentially, this will essentially bound like the size of S2 relative to S1, the boundary of S2 relative to the boundary of S. It will bound the boundary of S3 relative to the boundary of S2, and we pick up this essentially this boundary link property on each step.
And Nikhil, I guess you have a question.
Yeah. So Jason, I kind of missed why you were overlaying this expander every time. Like, shouldn't the expander decomposition already take care of that?
Well, you mean for the expander case or the single expander case?
Yeah, let's say even in the single expander. So some of the worry is that there'll be these balance cuts that you also want to detect later on, right?
So I guess here the issue was this balance cut was very small, and we were not able to guarantee that the balance cut was even at least like p times lambda, which is like the target mincut value. Right? And we want to force the balance cut to be large. And to do that, we just like overlay expander. The point is the balance cut increase has many more edges in the expander than the min cut itself.
Sure, I understand what it's doing, but like, why are we doing this?
So the reason is because we call our goal was to ensure that the min cut in G is a 1.1 approximate min cut in H, the same vertex partition. In this case, if the balance cut is too small, then this min cut here is not a 1.1 approximate min cut because this cut is like way smaller. It's like 1 compared to 3. So you want to force the balance cuts to be large, so that the min cut in G becomes which is a cut of in H of size roughly p times lambda becomes a min cut in H. Essentially, we want to ensure that the min cut in H is roughly p times lambda. Does that make sense?
Okay.
And,
yeah.
Which makes sense because like if we sample probably p, then the min cut should drop by a factor p.
Right. Okay.
And this just ensure that there are no balance cuts of even much smaller size. It's not the prettiest like solution to this, but I guess it works for a min cut case, and it does not work for a general 1 plus approximate cut Sparsification case.
Okay. Yeah. Thanks.
So Rasmus King asks, I think I didn't catch the age condition that was part of the sufficient condition for preserving cuts in the expander. Could you say that again?
Is this in the single expander case or the multiple expander case?
Is that right, Rasmus? And Rasmus, do you want me to bring you to the stage?
Okay.
Yes, single expander case. That's what he said.
Can you repeat your question? Sorry, I wasn't.
Yes, sorry. So I didn't catch the age condition that was part of the sufficient condition for preserving
this one
cuts in the expander.
The second one.
Yeah, could you say that again? Yeah, I guess the parallel age, I guess.
So this is essentially saying that for any UV, equivalently for any UV such that UV is an edge in the graph, the number of parallel edges in H. So essentially, the number of sampled edges. So consider like the set of parallel edges in G. Now, what Karger does is he just samples each edge with some probability into H, and essentially that's what we're trying to de-randomize. And this condition is just saying that the number of edges we sample in our de-randomization is essentially roughly what we should expect, plus or minus some small additive factor.
So Rasmus commented further that it seems too expensive to preserve.
So I mean, there's only m constraints.
Like too many edges, I guess. But I guess you're gonna set p correctly.
Yeah. So I think one thing you should notice: suppose a graph is simple. So suppose there are no parallel edges. Then this condition is actually trivial. Like there's nothing we really need to do because worst case this number of edges. The number of edges in H is 1. The original number of edges in G is also 1. But this quantity here is much larger. Let's say lambda is pretty large, relatively large. Essentially we get this condition for free. Yeah, this condition is only relevant for like super heavy, like many parallel edges. Like many more than, let's say, epsilon times lambda edges. Anything less than that, we can essentially get this for free.
Well, I guess yes, it seems Rasmus is happy now. I guess we can continue discussing with Jason in the social session, and so again, please stay tuned for that. Please stay for that. So let's thank Jason again for now. Thanks a lot, Jason. And yeah, we will start the launch in a minute.